Hello students, in this lecture we'll discuss the themes of group based on union and intersection of subgroups of group. So let's discuss first theorem. Prove that the intersection of two subgroups of a group is again a subgroup of prove that the intersection of two subgroups of a group is again a subgroup of a group. Proof is given. Given is let H and K be two subgroups of group G. If H and K are subgroups of G means H and K are subsets of G. So therefore, if H and K are subsets of G, then their intersection is also subset of G. Now our aim is to show that H intersection K is also a. Now to complete the proof, we will show that H intersection K is a subgroup of G. So let us take two elements belonging to H and K. H intersection K. We will apply lemma to complete the proof. X1 belongs to H intersection K. Definition of intersection: if x and y belongs to H intersection K, this implies x and y belongs to H and x y belongs to K. Definition of intersection of two sets. Now H and K are subgroups of G. Therefore, for x y belongs to H, x y not belongs to H. X y belongs to K, x y not belongs to K. So now xy, if xy belongs to H and xy belongs to K, this implies xy inverse belongs to H and xy belongs to K. This implies xy inverse belongs to H intersection K. So this implies for all xy belongs to H intersection K, xy inverse also belongs to HK. Lemma implies HK intersection is a subgroup of lemma. Now next one is prove that the intersection of any arbitrary collection of subgroups of a group is again a subgroup of a group. Prove that intersection of any arbitrary collection of subgroups of a group is again a subgroup of that group. So given let G is subgroup, and let's take a collection of subgroups H lambda belong to capital lambda. Let's consider set B any arbitrary collection of subgroups of G. Any arbitrary collection of subgroups of G. Take H is equal to intersection of all these subgroups of G. All H lambda belongs to lambda. Let's take H is equal to this. Now if H is equal to this, H is equal to this, we'll show that H is unity first and H is a subgroup. So since H lambda is a subgroup of G for all lambda belongs to lambda, therefore if a subgroup means it must have identity element. So therefore E belongs to H lambda for all lambda means E is the identity element all the subgroups. Lambda 1, lambda 2, lambda 3 to lambda belongs to lambda. So this implies if E belongs to all lambda implies E belongs to the intersection. E belongs to the intersection into we have to go the intersection of all the subgroups of G. We have to go this root H. So E belongs to H implies H is known. So H is known. Also we know that H lambda is a subgroup of G, is a subset of G for all lambda. So if H lambda is a subset of G for all lambda implies their intersection is also subset of G. Set theory. So what is this? What is the intersection? Yes, for this right. So H is subset of G. H is non-empty, H is subset of G. First and second implies H is non-empty subset of G. If H is non-empty subset of G, then we can apply lemma to show that H is a intersection of all the subgroups of the group J. For that, for H inverse of, we have to show not apply lambda, we will show this. Now for all AB belongs to H, all AB belongs to H, this implies all AB belongs to section of H lambda, lambda belongs to lambda, lambda belongs to lambda. So this implies AB belongs to, what this imply? AB belongs to H lambda for all lambda belongs to lambda. Now each lambda is a subgroup, each H lambda is a subgroup. Therefore, if A belongs to H lambda, then AB nodes also belongs to H lambda for all lambda. H lambda is a subgroup of G for each lambda. Now, if now interpretation, if AB inverse belongs to H for all lambda, we can write it as AB inverse belongs to the intersection because it belongs to all H lambda. So it belongs to the intersection, whatever number of these sets H lambda. So what it is? This is H. H was monopty subset of G, and AB inverse to H. Now let's discuss what about AB. We have concluded that if we take any number of subsets of a group, subgroup of a group, and the intersection is also subgroup, whether they are 2, 3, or any number. Now we will discuss what will happen if we take subgroups. What will happen to their union? Will the union of two subgroups is a subgroup? Now let's discuss it. The union of any two subgroups of a group is not necessarily a subgroup. I'm giving an example to support this statement. We have taken let a set H consist of 1 and 3, and K consist of 0 to 4. We have taken those two subgroups of are the two subgroups of this group 0, 1, 2, 5 under the operation of addition modulo 6. But the union of H union K will be equal to 0, 3, 4, 2, 3, 4. Is not a subgroup G. For why this is a subgroup G? Because if 2 and 3 belongs to H union K, but 2 plus 3 is equal to 5 does not belong to this. H union K. Implies this example that union of two subgroups is not always a subgroup. This is group. This is group under the operation addition process. Now our question is, when will the union of two subgroups is a subgroup? Now the thing for that is, the union of two subgroups of a group is a subgroup if and only if one is contained in that. When will the union of two subgroups will be a subgroup? Subgroup if and only if one is contained in the other. Either first is contained second or second contained first. So if and not necessary part. Let us suppose that union to subgroup is a union to subgroups is a subgroup. Now our aim is to show that one is contained in others. Now let's suppose that let H1 H2 be two subgroups of a group G such that a H1 union H2 is a subgroup. Now to prove, what to prove? Our aim is to show that either H1 is subset of H2 or H2 is subset of H1. Now prove by contradiction again. If possible, suppose H1 is not a subset of H2 and H2 is not a subset of H2. And H2 is not a subset of H1. H1 is not a subset of H2 and H2 is not a subset of H2. So since H1 is not a subset of H2, what does this imply? This implies, so there exists a belongs to G such that A belongs to G such that A belongs to H, but it does not belong to H2. Similarly, again H2 is not a subset of H2. H2 is not a subset of H1, so there exists a B belongs to G such that B does not belong to H1 but belongs to H2. Since A belongs to H1 and H1 is a subset of H1 union H2, so A belongs to H1. You can see this result by drawing Venn diagram of set theory. Things will become very clear to you. A belongs to H1, therefore H1 is subset H2, therefore A belongs to H1. Similarly, B belongs to H2 and H2 is subset of H1 H2, so B belongs to H1. First and second implies this first and second implies A and B belongs to H1 union H2. And H1 H2 subgroup, therefore AB inverse also belongs to H1 H2. What does this imply? This implies if AB inverse belongs to H1 union H2, this implies AB inverse belongs to H1 or AB inverse belongs to H2. Now, case first, let AB inverse belongs to H1. Since A belongs to H1, H1 subgroup, therefore inverse also belongs to H1. A belongs to H1, H1 subgroup, inverse belongs to H1. Therefore, on a closing property, A inverse belongs to H1, AB inverse belongs to H1, therefore A inverse into AB belongs to H1. Closing property of subgroup is H subgroup. H is subgroup. H1 is a subgroup. Now, A inverse to E, this implies B inverse belongs to H1. If B belongs to H1, B H2 subgroup, the inverse of B, inverse of element also belongs to this. Inverse of B, inverse of B also belongs to H1. That is, B belongs to H1, which is not true. The case, this case is not possible. This case not possible means H1 is not a subset of H2. H1 is not a subset of H2. Similarly, we can prove the second part. Similarly, this case is not true. Similarly, with the second part, AB inverse belongs to H2. This is it. AB inverse belongs to H2. AB inverse belongs to H2 and belongs to H2. So AB inverse closure property, H2 is a subgroup. Closure property AB inverse B belongs to H2. So AB inverse B inverse B implies A belongs to H2, which is again false. False. This case is also not possible. Both the cases are not possible. Therefore, our supposition is wrong. Hence, either H1 subset H2 or H2 is subset H1 if union of two subgroup is again a subgroup. Now, converse part of this. Suppose either H1 subset H2 or H2 subset H2. This implies if H1 is subset H2, then H1 union H2 is equal to H2. Because this is contained in this. H1 is contained in this. So H1 union H2 will equal H2. If H2 is contained H1, therefore H1 union H2 again H1. So H1 union H2 is equal to H1 and H1 union H2 is equal to H1, H2 and H1. This implies H1, H2 is a subgroup of G because H1 and H2 are separate. Since both H1 and H2 are